Cool. All right, gang. We're back. It's Overview Episode 2. We got Tag.
What's up, guys?
We got Maggie.
Hey.
And we got special guest Alexandra.
Hello.
We are going to jump into some cool chat about space origami, I guess a bit about your background, some of the research that you do here in the department. Before we do that, I should just say thoughts and opinions are our own. We don't represent any particular lab department or the school of Stanford University during the next 30 minutes of interview. But yeah, we'll get into it, but I kind of want to eat dessert first because there's some cool stuff on the table in front of us. And I would just love to know what it's all about. Yeah. What's some of the cool stuff we have here?
All right, I brought lots of props.
All
Don't know where to start.
How about
the dragon? Yeah.
Not sure. All right.
Yeah.
I am an origami enthusiast, I guess you could say. So I've been folding complex stuff probably since middle school-ish. And then somehow wound up doing that as my PhD.
Somehow that's an aerospace PhD right there. It's crazy.
Yep, this is where you can start. So this one here, this is one of my favorite artists. If you want to front on that. But his name is Satoshi Kamiya. Sorry if I'm butchering that. He's a Japanese origami master. This is his ancient dragon, the newer version that has teeth, as of a couple years ago. I have another one of his works here, which is it's called the Ryujin.
Has scales on it?
That guy has scales.
Wow.
It's a simpler version. It's a more complex version. This is a 2.1. There's a 3.5, which has scales on the legs as well, which I hope to fold this summer if all goes to plan.
I feel like we got Isaac in dad mode here pulling out the
It's like the dad of the barbecue, just like taking pictures of the sausages and stuff.
Yeah, and also I thought I'd bring this. This is what the scales are supposed to look like if I would fold it out of an actual like large sheet of paper.
That's
so
great.
That would kind of cover the
Mind if I pick this one up? I want to hold it up close to the big camera real quick.
Yeah.
Go for it.
So how did you get into this?
Mostly YouTube, honestly.
Okay.
I mean, I had, as a kid, I had the like little origami books that still involve cuts and are potentially real origami, not sure.
Oh, okay.
Some little sus moves there.
If you make a cut, it's like not technically origami anymore.
Technically, it's kirigami, origami hybrid sort of thing. Not real traditional origami anymore.
Cool.
And then I just found some YouTube channels that had tutorials for this stuff and went from there.
Yeah, well, you kind of alluded to it. I mean, so at the overview, we talk about like fields of aerospace engineering, and we deal generally in, like that aeronautics, aerospace, our audience are students that want to get into the field or just people who are sort of interested about the science. And how does, I guess what we're looking at here, this like really complicated origami relate to, the space sciences? Like, how is this practical in space, essentially?
I mean, that is the question. I guess the main place it comes into play is when you want big structures that need to fit into a rocket. Because rockets, with current technology, the largest they get is about a 5-meter diameter. Mm-hmm. So that's maybe the size of this room, a little bit smaller than this room. And then anything that you want to launch into space has to fit within that rocket fairing. Mm-hmm. But if you need things like antennas, solar panels, solar sails, of course, as we get farther from the sun, get further from Earth, communications, things are longer range. We need bigger solar panels, bigger antennas. Things need to get larger. And that doesn't tend to fit in a rocket anymore. So for probably since the 1900s, late 1900s, engineers realized that they can use origami concepts and the kind of rules that come with folding this sort of complex stuff can also be transitioned into how do we fold this kind of large structure in an efficient way. And kind of the keys are making sure it can deploy reliably in space. So we have to be able to model it, predict it. You can't just kind of crumple it up into a ball and then hope it, makes its way into the final shape in space. It has to be, done in a very controlled way.
Yeah. It's maybe
that's why.
I was just gonna say, it's maybe a dumb question, but just to that point, like, how one-to-one is it with origami? Because I kind of get like there's some structures, like if you wanted to unfold like a star sail or some sort of like, really thin reflector, it would kind of be like folding and unfolding paper. But then something like, I'm trying to think of what a good example, I guess James Webb Space Telescope or Starshade we might have a chat about. I think concepts that people might be familiar with. But those are, it's like panels and stuff, right? So that's like a brick, right? So how, I don't know, is that like origami? It's thick, right?
There's actually a lot of research on how do we fold thick things.
Okay.
And it usually involves, actually that's why I brought this.
Yeah.
This is a This is basically, it's an origami pattern. It's kind of it's not really origami anymore. It's a set of tubes, basically, that can be folded flat. But if you want to make them thicker, there's a lot of different techniques of how you kind of shift the hinges and kind of mess around with the thickness such that you maintain kind of the location.
Hold on. Isaac back in bad mode. For those who aren't watching or just listening, she just pulled this thing. It looked like a solid brick to me. Now it's suddenly got like tunnels in it. Describe it to us. What's going on here?
This is called the Miura Ori zipper coupled tube. It was designed, the Miura Ori pattern designed by, I forget his first name, but the engineer named Miura, and Ori, I guess. But then this actual kind of tube coupling structure was designed by Evgeny Filipov, who's at University of Michigan. Hopefully I said that right. And it's kind of a method for this tube structure has surprisingly high out-of-plane stiffness. So it's very solid kind of in this direction.
Right.
But at the same time, it can fold completely flat like this. And if you use a different method of thickening, it can actually flatten in the other way as well. It doesn't work with this model.
Would you mind unfolding and folding that again? It's just so satisfying when that. So this is something you 3D. How does this manufacture? Like, how do you?
Yeah, so these are 3D printed panels. It's cool because this entire structure is basically just 2 unique panels, and they're mirrored parts. And then it's taped together along the hinges, which is.
I was gonna say, is that just normal tape or?
There is an ongoing battle in the origami community to find the best tape for this kind of application. So far, Robert Lang, I assume he'll come up later, but he's the origami physicist. He's kind of the father of the origami in space field. But he swears by this stuff. It's actually Spinnaker, wait, is that correct? Yeah, Spinnaker adhesive tape. It's used for fixing the sails of sailboats.
Oh.
So it's basically a very thin fabric with a good adhesive on it. So it's very strong in bending. It's basically fabric.
And so this is how you fit a structure into a rocket, is you have that folded up state, and then once it gets out, you get rid of the payload fairing and it's in space, then it can, has some probably electronic mechanism to help it expand, and I'm guessing very specific set of instructions on like how to expand in order. Yeah,
there's a couple different methods. The cool thing about a lot of origami structures is that there's so-called 1 degree of freedom in terms of the unfolding, which means if you unfold just one segment of it, the entire thing unfolds. Wow. So you really only need one actuator to do the entire unfolding process, which is the same for kind of these larger structures as well, which is really convenient because, I mean, obviously you need redundancy, but it kind of unfolds itself almost.
Mm-hmm. And how long have we been doing this? Because I know, like, I heard about James Webb Space Telescope when it was deployed, it had like different process and stuff, but like, is this how we also got like solar panels on the ISS even? And like, because you said it's been going on since like the 1900s, engineers have been looking at this stuff. Are pretty much all of these space things we know about, do they employ origami principles?
Not necessarily origami, but the larger field is called deployable structures.
Okay.
So basically anything that needs to be kind of condensed somehow.
Mm-hmm. So folding in half, you're not calling that origami. And
like if you look at like InSight on Mars, they had those kind of fanned panels. Like, I guess you could say that's origami. They kind of, everyone's made it.
Probably my level of origami that I can.
Or like on the ISS, they have it's called ROSA, the Rollout Solar Array, which is kind of a prototype done by, I shouldn't say company names in case I get it wrong. I think it's by Redwire. And it kind of, it basically is a rolled up array, as the name suggests. And then they have these composite booms that then just kind of unfurl it. So these sort of concepts have been in play for quite a while, yeah.
Awesome. So as we're going into the future, is it just like thinner materials, like, tighter folds? What's the direction of complexity for this field?
There's quite a few different directions, all of which are cool.
Yeah.
One is kind of moving away from origami, but like self-assembling structures. So more kind of controls, robotics, how can we modularize this kind of stuff? Which, I mean, even this is part of a research project where kind of each of these modules, we can have their own material properties, their own kind of functions, electrical components. And you can kind of combine them all together, stack them up in a way that preserves its folding capabilities. So yeah, self-assembly is one. Another one is kind of morphing structures or live structures. They're basically structures that can kind of modify their shape in space. Especially useful for antennas if you want to kind of change the directionality or the oh boy, antenna terms. You don't know about antennas.
Yeah, by changing the structural properties, you can change, more complex properties that we might be interested in adjusting.
Yeah, or even
some
if it
reason.
if it doesn't deploy kind of fully into, if we don't want to care as much about how accurately it deploys and having it be able to kind of tweak its shape
Yeah,
on orbit, is very interesting. Some robotics stuff, especially things like swarm robotics, swarm exploration, where you want to fit hundreds of kind of tiny robots into a spacecraft, get that to some other planet or the moon, and then obviously the smaller these robots can get, the more you can pack in.
Yeah, I guess it's about efficiently using that space that you have, right? I mean, I was thinking as you were talking a bit about some modern companies doing it, and you think about like new space, and everyone's paying for like a cubic meter or a pound of like stuff to go to the moon or up into space. You don't want to waste an inch of that, right? You just want to completely jam pack it with.
Yeah, but that's why this is useful not just for like huge antennas, but also for CubeSats, where you need to you want probably a decent sized antenna on that thing to be able to go farther into space, but you still need to
Every
fit into
kilogram you're setting up is probably more than all of our graduate stipends for our entire PhD combined times 10.
Yeah. Oh, it's cool about the small stuff, but you got one more toy in this box of tricks, and it doesn't look small. I'm interested in what this is.
Yeah, so let me scooch some stuff around.
Yeah.
So let's start with the big one. This is the more easily foldable one. So I worked on a project called Starshade at JPL for almost 2 years, which is basically a huge sunflower-shaped disk that would fly information between a telescope and some distant star of interest. And it would block the light of that star from reaching the telescope so that we could basically better see with higher contrast any planets around the star. And this thing would have to be, there's kind of a range of sizes, but on the order of tens of meters in diameter, and very, very accurate in terms of its shape once it's deployed. So this is the inner disk. The actual thing is twice this size. And this is a 1/10 scale model of that.
Oh.
So you move things around. But
Oh, wow.
Oh, yeah. It's awesome.
That's so cool.
So this would and this is made out of rigid panels.
And this is the same shape as Starshade, like the actual Starshade?
So the inner disk of the bigger structure is a disk, and it has kind of these petals that come out. It looks like a sunflower. It has 24 to 28 petals, and those are also kind of almost twice the radius. There's some very interesting optics that goes into kind of deciding the exact shape. But I was just looking at my project was designing this edge part that would interface with the truss that's unfolding this, that is connected to. So this is all the actual code for the inside of this is my advisor's work.
Oh, awesome. Yeah, so again, if some people might just listen to this, but I don't even know how to describe what we're looking at. It's sort of like a big spiral flower, but it folded up into the space of about, sort of 2 fists wide. And now that you've unfolded it, it's on the better part of the meter.
Coliseum before it was unfolded. Now suddenly it's this big sunflower.
Yeah, and you mentioned these are actually, like there's some thickness to these
so
things
that's
here.
it's kind of hard to see, but there's basically these little cuts in between. The panels don't actually line up. That's not because I'm bad at taping. That's also part of it. But there's basically these little gaps in between. And those allow for, when it's folded, it basically allows for a little bit of play in these hinges so that the thickness isn't a problem.
Oh, right. So that's all very deliberate, huh?
Yeah, so it's basically leaving kind of little gaps. I don't know if it's even visible, but...
I'm curious, how much simulation or like modeling on computers do you use for this? Do you typically like prototype it first with like paper, and then you're like, oh, this kind of works, and then you move to a more complicated cardboard structure, and then you work on the computer? Or like, what is the process of creating this?
I think it varies greatly. This is a very good question. And it's also one of the things I enjoy a lot about doing this work is that it kind of involves simulations, involves design work, kind of coding up algorithms, and then also prototyping, all of which I enjoy. It's kind of do a little bit of both, of everything. But to answer the question, it kind of varies on the structure. I think, especially with things that are flat when they're unfolded, it's really easy to be like, I'm just going to make a prototype real quick out of some printer paper to make sure it works. But then if we actually want to analyze kind of the stresses and the like deformations that happen in this structure as it's unfolding, then we definitely we do simulations. There's also, they can be finite element simulations, which are obviously more costly, but there's also a lot of kind of simplified models of these structures that can be used to get kind of a very basic idea. There's one I included in the article, actually. It's called Origami Simulator. It's free, online, and you can basically just give it any crease pattern and it'll fold it live.
Yeah, and this article, by the way, is the article in the overview.org, so you can read it there. And it's also referenced in like one of the newsletters that we put out every other week in the morphing newsletter.
I love the name.
Yeah, it's definitely worth checking that out if you want to get into more detail, because we won't touch too much on the technicals, but you go through some of the actual scientific principles and stuff that go into making these folding structures possible. And I believe you also gave like a file that you can load up onto the origami simulator, and you can just like control it unfolding. It's not quite as satisfying as seeing it in person, but it's 95% as satisfying.
Yeah, the fact that they have that whole algorithm running, you can just mess around with origami online is super cool. And I think that's also kind of the cool part of doing this work now, is that there's these tools where you can just see if your thing folds without actually having to get out paper.
Yeah, so we've kind of covered, we've got sort of this end of the table that I'm seeing. We've got these, folded dragons and like stuff that you've done like more on the hobby side.
We ate our dessert first, as you said, right?
Yeah, exactly. Dessert first. I mean, this is just as tasty though. But yeah, and there's, now we're talking about stuff for Starshade and like actual space projects and these sort of folding structures that seem much more practical and less artistic. But what's the jump between? Like I get, as a kid you can be into origami and you get a book and like it's fun, and you can start folding this really complicated stuff. But how does it, I don't know, how did you get from there to, doing it for JPL? Like it seems like a big jump. I'm sure our audience is interested in how you do a jump like that. I
mean, from one side it was a lot of luck.
Yep. Always.
I met the right person at the right time. But I guess the progression was I was getting into this stuff probably middle school, more seriously. And I came across this TED Talk by a guy named Robert Lang, who I mentioned earlier. And he kind of really went into the math behind it. And he was like, yeah, here's kind of the rules that govern these fold patterns. And here's kind of how we can apply that to space. And at that point, I had no interest in space. I had no interest in space until I started undergrad, basically. I was looking to go into computational biology and neuroscience and stuff like that.
Oh, wow.
Quite the shift that happened there then.
Yep. I loved kind of folding origami in my own time, and that was where it was going to stay until I started at Caltech. And I met my now advisor, Manan Arya. He gave a presentation called like Engineering Origami in Space. And one of my friends who knew I was into origami was like, you should probably go check that out. It seems interesting, Mm-hmm. I was looking for summer research at the time. So I showed up to his meeting. I watched the presentation. I was like, this is a thing I can do? I didn't know this field was a thing.
I can do my hobby for a career and like real-time research and...
Yeah.
What? I was like, I guess I have to do this.
I'm trying to think what that equivalent would be for me or for you guys, if someone's like, hey, you can do triathlon for space exploration, we need you to ride a bike to Mars. I'd be like, sign me up, but I don't know. What would you guys say? Like, what are your hobbies playing into your career at all?
Not even in the slightest, but...
You can't climb Half Dome to the moon?
Listen, maybe one day.
There's plenty of fun climbing opportunities on the moon.
True.
A lot of rocks.
Fingers crossed for that. But, that's so funny that... Well, a few things. So, hold on, you were actually in your undergrad already, and then this came along, like in sort of that first year. And you were at Caltech, right?
Yep.
Okay. And it just so happened, because Caltech sort of linked up with JPL a bit, and Dr. Arya was...
Yeah, so Dr. Arya was... Yeah, so honestly, from when I got to Caltech, I was very drawn towards JPL. Like, you can't have something that cool be that close and be like, I'm going to do bio.
Is it technically on campus? Like, JPL and Caltech, they're like
30
touching,
minutes
right?
apart.
30 minutes? Okay, 30 minutes apart? Okay.
It's not quite, but there's a lot of, most professors, not most, but a good portion of, especially Mechie and aerospace professors at Caltech also work at JPL. There's a lot of overlap, especially between the facilities and tools and things. So it's very easy to get involved, which is really cool for an undergrad program. So yeah, actually, though Dr. Arya's presentation was through the international program, so it wasn't even related to either of the mechanical or aerospace departments. It was just because he's Canadian, so he was like, here's my path into aerospace, basically. But I went up afterwards, I talked to him, like, hey, is there a chance I can work with you over the summer? Like, what resources do you recommend if I'm interested in kind of pursuing this? And I mean, somehow things came together. He was the only person I asked to do research with that summer. So I was screwed if that didn't work out.
And was that your freshman year that you did that?
Yeah, so this presentation was, I think, in November or October of my freshman year.
So you were just been in school for a couple of months.
Yep.
So was that intimidating to walk up to a professor who's like was he a professor at Stanford at that time?
He was working at JPL.
He was working at JPL. Okay. Did it take some nerve to go up to him and be like, hey, can I do research? Because I think me as a freshman, I would have been like, this guy works at JPL. Am I allowed to talk to him? You know, like, I'll still feel this.
I was definitely shaking, sweating bullets. I was like,
What gave you the confidence to go up and ask him, or did you just kind of push through the
I was
nervousness?
really, because there was a friend who was there with me, and like we watched the presentation together. Eventually, I was just like kind of wandering around the room afterwards, like trying to avoid going up to him. Other people were talking to him, and then eventually that friend left, and I was like, what if I just email him later? And then something in me was like, it's not going to happen if I just email him later.
Yeah.
I feel like you need to have that face-to-face contact. Like that was the opportunity.
That was the devil and the angel on your shoulder. Just email him later and then I'll go up and talk to him. Yeah.
Yeah, so do you have any advice for people who maybe are interested in kind of random fields? Like, how do they kind of understand what their interests are when they're undergrads? And how do they take the leap of faith as you did?
I honestly don't know if I'm the right person to answer this question because I feel like once I kind of got into that internship, it was a straight path. Like I did not look back.
Yeah.
That's interesting
But
that
I
you didn't look back because maybe, I don't know how invested you were in comp bio, but
Clearly not very much. I think because in Caltech, we only have to declare a major after the first 2 terms. It's kind of in the spring. So I was already mechie by the time that hit by
cool.
far.
And as far as you know, I mean, Mechie is the major to do this kind of work in, right? Like that's what
We just
space origami
didn't
would
have
fall
an
under.
undergrad aerospace program.
Oh, right. Yeah, yeah.
So it had to be mechanical. But I mean, it's in terms of kind of learning the like structures parts of it, because I mean, this all falls under the structures category. I think, Mechie aerospace is kind of there's plenty of CS people. There's plenty of math people. I mean, origami is huge on the theoretical math as well. So it does really span a lot of different fields, which is cool.
yeah, so it sounds like origami has like the math component, the programming component, the hands-on component. Like which one speaks to you the most? And I guess which one do you spend the most time on? And which one have you like worked on developing the most?
Good question. I love anything hands-on. I could not sit at a computer all day. Like my brain would rot. I need some
Some
sort
of us do that.
Our brains are rotten.
Yeah, wait,
I just mean personally. Like I need to have some.
the brain still rots when I'm sitting at my computer all day, but
I need to have some sort of kind of. I'm very fidgety. Like I need to be able to kind of mess around with something. So I feel like that really appealed to me. And I think I know one topic I talked about in the article as well is kind of how does art play into science. And I think for me, I'm like a very visual spatial person. And I think that a lot of engineering, like even if it's not structure stuff, there's a lot of kind of, you need to be able to visualize kind of the problem, what's happening, kind of how these 3D parts are playing together. And I think a lot of kind of artistic skills also have that same mindset, or that skill is useful for a lot of artsy things as well. So that's one of the things that really appealed to me in terms of being in kind of mechie and the aerospace field.
some of that appeals to me too, because when I do like CFD, I love to do photography, and for me, you know, I joke that CFD, well, everyone jokes that CFD is colorful fluid drawings, you know. And to me, I think like sometimes that artsy side, I feel like plays into engineering, and it helps me enjoy, and it helps me visualize, and it helps me be a little bit creative with like what I'm doing. Because I feel like there is beauty in engineering, there's art in engineering. I think this is like the ultimate example of it, you know, that like art is a part of STEM. It can be a part of engineering. I even saw, I think Isaac here is proposing a new acronym for STEM. I saw this. Yeah. I wanted to make sure we hit that. This is a cool new acronym for STEM.
Had the A in STEAM. Yeah, no, it's not mine. It's a thing that's
So science, technology, engineering, art, and math.
Yeah.
Yep.
I think to your point, I mean, the kind of skills that you develop with the sort of hands-on, like recreational type stuff, like origami, but there's a million other ones, it just ends up being super, super useful. And how often do you talk to people like in the department, particularly in the sciences? It's like, why are you interested in this field? And it's like, oh, because I had some little like engineering kit, or I made like little model planes or something like that. It just always ends up driving, what you actually end up doing. Yeah, I have a bit of a bone to pick. Hold on, there's something that I just realized in the article. You said in the article that you were an artsy kid growing up. But then you went to Caltech. Last I checked, Caltech does not have a particularly strong arts program.
They're not a
I
liberal
was
arts
an
school.
artsy smart kid.
Artsy smart kid.
I
Okay.
just didn't want to be too.
yeah.
Because I mean, both my parents are engineers. I kind of grew up, around Legos and Connects and construction kits, and yeah. So I was always into the like technical stuff. I never wanted to go into art as a career. It was kind of just something I enjoyed doing on the side. So I knew it was going to be something in engineering, either kind of computers or robotics or something like that. So kind of, I loved doing the like artsy, art projects. I always took art classes in high school and before that. So I was artsy in that sense.
Yeah. No, I just wanted to clarify.
It sounds like how you got into this was very instinctual. Like it seems like it was like a gut feeling, right? And then
Sometimes
just,
I'm worried it's
followed
too
that.
much of a gut feeling. At some point I'm going to hit the end of the road and be like, what have I done?
Yeah.
Why am I here?
I guess, is that how you kind of make your decisions and how you've done that so far? And have you like made decisions in other ways kind of in your career, or like even coming to Stanford, was that also a gut decision sort of?
I mean, yes and no. I think I definitely, because I'd worked with Professor Arya before, and I knew kind of that worked well. I loved the kind of the research he does. So in that sense, Stanford made sense for me. But I definitely, I think it's a good idea to kind of explore options. Also, going back to your question about kind of how do you figure out what you're interested in and kind of how to, I guess, work hobbies and other random things into a weird field you found. Just trying lots of things and like exploring all options. So even though I like had this gut feeling of like, this is what I want to do, I like talked to other research labs on campus. I kind of, back in undergrad, I looked at kind of, if I go a little bit kind of off into more materials, what would that look like? And it just never really sat right. I couldn't get as kind of excited about the project as folding origami.
Yeah. Do you know if you want to continue on like folding origami in space, or is there like any other applications that you're interested in, like maybe on Earth, like construction, or I don't know, any other like applications that appeal to you?
I mean, definitely. And also, before I fully answer that, I answer the second part of your first question of kind of, is it just gut feeling? I think it's also important to kind of think about, what the next steps are. Like, is there a career I can actually do in this?
Yeah.
Are there companies that are hiring kind of in the deployables field?
So it's also very practical, you're saying.
So I've definitely, maybe not quite as practical as I would like, but there's certainly a interest in this stuff kind of in the greater industry. And I think that's also really important to keep in mind.
Yeah.
Not just being like, this is fun, I'm going to do this for as long as I can, and then who knows. What was the first part of the question?
Like in terms of instead of just doing this in space, are you interested in other applications?
I'm definitely, there's some interesting work going on, both on the like biology side. As you mentioned, the construction side, there's some interesting someone who's trying to like make a boat that's origami inspired. There's a company called Oru Kayak. It's like an origami inspired kayak. The whole thing folds up into this little like briefcase, and you just unfold it and have like.
But if you hit like a rock or something, it'll just like fold in and like smash in.
Strap it down.
Oh, okay.
It's pretty solid.
Wow.
You like strap it
That could
together.
be useful if you go backpacking, right? Fold up your kayak and put it in your backpack, and yeah.
Quite that small, but it's good.
The
There's
crew.
some, like,
Oh, sorry, go on.
good.
I was just going to say, I mean, the group cohort, goes camping a lot, and whenever we're unfolding the tents and stuff, and Alexandra's there, I'm always just like, deployable structure. It's origami,
So someone's got to come with a tent.
Me folding my tent is not origami, though. That is, like you said, that's crushing it into a ball and shoving it in. Yeah.
No, there's some prototypes of like cool origami inspired tents. There's people working on like a lot like interactive building facades that like depending on the sunlight they like change their shape, like how much sun they let in.
Oh, wow.
There's people looking at on the medical side, heart stents. So kind of they fold up really small, can fit through your arteries and kind of expand in the desired location. There's another group at Stanford, Renee Zhao's group, who's doing these little they're called spinners. Basically can be used to deploy drugs to a very specific location in the body, or also to suck out blood clots from arteries. Also kind of origami inspired work. I'm definitely missing stuff, but I'm definitely drawn towards the space as of now.
That's cool.
No, that's super cool. We're sort of coming up on time. I think we've been gabbing for about half an hour here. I had one question that I wanted to get in that we haven't got to yet. I think I can still fold an origami crane.
Okay.
How much harder is it to fold one of these than that?
Significantly.
Significantly. Cool. I think that pretty much gets us to the end. I mean, if people want to find you and read more about what you've done, I mean, they can check out the article at theoverview.org. And I guess LinkedIn is probably the best sort of social to connect up with you on if they want to ask questions and things.
If I'm on there.
If you're on there, yep. If you're not too busy folding stuff. Yeah, cool. I think that pretty much takes us to an end, but thanks for your time.
Yeah, thank you for having me.
Alexandra, everyone. Yeah.